As scientists explore the microscopic universe, they find it's governed by rules that are often incomprehensible to those of us in the normal world. At the smallest scales imaginable, not only does information appear to travel faster than the speed of light, but human observation often seems to decide what happens.
It seems like the behavior of quantum mechanical stuff is different when we're looking at it than when we're not looking at it.
This profound conclusion comes from performing the double hole experiment. Scientists first conducted this experiment a century ago, firing photons of light through a metal plate with two slits. The light that went through the holes hit a screen behind the plate. Does a microscopic particle spontaneously clone itself in midair? After years of study, scientists still don't know exactly what's happening.
Probably the most magical thing is that in quantum physics, an object can be in more than one place at the same time.
It actually can sense both slits and actually go through and quantum mechanically feel the structure of both slits in the experiment.
Most physicists agree that the math is quite solid and leads to solutions that are undeniable and can be confirmed with experimental measurements. But exactly what is happening and how is a matter of debate.
To try to grasp this amazing experimental result, scientists decided to observe how individual electrons behaved when they went through the double slit. How exactly could a particle go through both holes at the same time?
Scientists got a front row seat to observe the strange behavior of these electrons or other subatomic particles or even photons of light. Doesn't really matter as long as they're small. They didn't just look at where they landed on the screen back there. They also watched the behavior of the particles as they went through the holes. And then they saw something amazing. When scientists were watching the holes, the electrons behaved like particles, forming the baseball-like pattern on the screen back there. But when the scientists weren't watching, then the electrons behaved like waves. They formed a pattern that looked like the interference pattern produced by waves on a screen. That's really strange. What you see depends on whether you're watching or not. If you're watching, you see the particle-like behavior, like baseballs. If you're not watching, you see a wave-like behavior, but not both at the same time.
This was nothing less than astounding. Observation seems to change the nature of subatomic particles.
Mysteriously, when we're not looking, things are waves. When we are looking, they look like particles. So even an electron, which seems to us like a particle, has wave-like properties when we're not looking at it.
The fact that when we don't look, the electron appears to go through both holes, but when we do look, we always see it go through one hole or the other, is what we call the quantum enigma.
How could our decision about whether to observe something change how that something acts? There is a technical explanation.
To make an observation, you somehow have to interact with the system. For example, you have to shine light on it, which then bounces off and you observe the light. That's how we can tell that a baseball is here or there. We bounce light off of it. Well, for macroscopic particles, that doesn't disturb them very much. But for microscopic particles, the act of bouncing the light off of the particle changes where it is and how it's moving.
So in the microscopic universe, where photons of light are about the same size as subatomic particles, these photons have a big impact when they illuminate the particles so we can see them. But this doesn't answer the question. Why doesn't the light simply change the direction of the subatomic particles? Why does observation actually change the nature of what is being observed? However, the double hole experiment's mind-boggling conclusions don't end there. In recent years, technology has allowed scientists to perform a fascinating variation of the test. Its results call into question our perception of time itself.
This is like a high-tech version of the double hole experiment. Electrons are being fired toward a barrier with two holes in it. But the scientists can delay their decision about whether to observe the electrons until after they've passed through the holes, but before they hit the screen. It's as though I'm on a baseball field, and there's a baseball being pitched toward the barrier with the holes in it. But my eyes are closed, so it goes through, and it behaves like a wave. But then, at the last second before it hits the screen, I open my eyes and decide to observe it.
At that moment, the electrons, in essence, become particles, and seemingly always were particles from the time they left the electron gun.
So it's as though they went back in time to before they went through the holes and decided to go through one or the other, not through both as they would have had they been behaving like waves. That's really crazy.
That's the enigma. That our choice of what experiment to do determines the prior state of the electron. Somehow or other, we've had an influence on it which appears to travel backwards in time.
Scientists are only beginning to grasp what these microscopic mysteries mean for time travel and changing the past in our everyday world. But one thing is clear. The rules that govern this subatomic world hint at a universe that's just as mysterious as science fiction. In fact, quantum physics may suggest that reality is simply a figment of our imagination.